This is section 10.2, similar triangles and the Pythagorean theorem. What do you notice about these pictures? You're probably thinking to yourself that they're the same, but in each case, one is bigger than the other. You would be correct. What do we call figures like this? Well, we actually call them similar figures. Figures that have the same shape, but not necessarily the same size. Specifically, we're going to talk about similar triangles. Similar triangles are ones where corresponding angles have the same measure and the ratios of the lengths of the corresponding sides are equal. Now, this concept of corresponding angles and corresponding sides is very important. Let's look at the two triangles below. These are similar triangles. Let's understand why. First of all, we have to match up our corresponding parts. It's true that angle C corresponds to angle F, angle A corresponds to angle D, and angle B corresponds to angle E. So what that also means is that the side measuring 6 inches in this triangle corresponds to the side measuring 3 inches in that triangle. The side measuring 8 inches in this triangle corresponds to the side measuring 4 inches in this triangle. And finally, the side measuring 4 inches in this triangle corresponds to the side measuring 2 inches in that triangle. So according to the definition of similar triangles, our corresponding angles all have the same measure. So angle C and angle F are congruent, angle A and angle D are congruent, angle B and angle E are congruent. Further, the ratios of the lengths of the corresponding sides are equal. Let's take a closer look at this. If we take the ratio of 6 inches over 3 inches, we'll get a ratio of 2. Our next set of corresponding sides have measures of 8 inches and 4 inches, and again, we get 2. Our final pair of corresponding sides have measures of 4 inches and 2 inches, and again, we get 2. So because our corresponding angles are congruent and our corresponding sides have equal ratios, we know that these two triangles are similar. Recognizing similar triangles can get a little bit tricky. In our first box, top left, we can see that these two triangles are similar. They have the same shape, but not the same size. Things get more difficult, though, when the orientation of one triangle changes. Let's look at our second box over here. These are the same two triangles, however, triangle FED has been flipped. Would you still recognize these as being similar triangles? Let's look at our third box, bottom right. Again, these are the same two triangles. However, triangle ABC has been flipped upside down. They are still similar triangles. And our final box is probably the most tricky scenario, where one triangle is inside of another triangle. In this case, points B and E are the same point down here. And you can see that triangle FDE is lying inside of triangle ABC. But they are still similar triangles. Now let's talk about right triangles. Let's define hypotenuse. It's the longest side of a right triangle, and it always is opposite the right angle. You can see the diagram below. The hypotenuse is the longest side and it's opposite the right angle. Opposite means it's across the triangle from it. The legs are the two sides that form the right angle. In the diagram below, you can see the two legs that intersect to form the right angle. Next, we'll talk about the Pythagorean theorem. You've probably heard of this before and have used it many times. It states that the sum of the squares of the two legs equals the square of the hypotenuse. The Pythagorean theorem is often represented as a squared plus b squared equals c squared, where a and b are the legs of the right triangle and c is the hypotenuse. The Pythagorean theorem is used to find the length of a third side of a right triangle when you know the measures of the other two sides. Let's take a look at an example that uses the Pythagorean theorem. Did you know that a television is measured by the length of its diagonal? This is a 25-inch television set. The length of the screen's diagonal is 25 inches. If the screen's height is 15 inches, what is its width? Well, you can see from the television picture that we have a right triangle. The diagonal of the TV is our hypotenuse, and then our legs are made up of the vertical and horizontal sides of the television screen. Of course, we're assuming that the vertical and horizontal sides form a right angle, which is a safe assumption because of the way the TVs are made. Since we know two of the three side measures, we can use the Pythagorean theorem to solve for the third side. So let's start with our Pythagorean theorem. A squared plus b squared equals c squared. We know a and b are the legs and c is the hypotenuse. Let's plug in 15 and 25. 15 is one of the legs, so we'll plug it in for a. 15 squared. We don't know the other measure of the leg, so we're leaving b in the Pythagorean theorem. And finally, we know the hypotenuse is 25, so we put 25 in for c and square it. Now we need to do a little bit of algebra to solve for b. You may choose to start out by squaring 15 to 225 and squaring 25 to 625. The next step would be to subtract 225 from both sides of the equation. This results in b squared equaling 400. Now to solve for b, we have to take the square root of both sides of the equation. This leaves us with side b equaling 20 inches. So we know the width of this television is 20 inches. This has been section 10.2, Similar Triangles and the Pythagorean Theorem.